Welcome back, everybody. It's my pleasure to introduce to you our next speaker, Professor Jeff Shamma. Professor Jeff Shamma is a leading control theorist, until recently a professor at Georgia Tech, and more recently at KAUST, King Abdullah University of Science Technology in Saudi Arabia. A very special institution, as a matter of fact, that I had the pleasure of visiting a couple of years ago, that's designed and modeled to operate at the same level as top research universities in the US, for example. Professor Shamma has many significant contributions that have garnered several awards, including the coveted Donald Ekman Award. His interests range from nonlinear and adaptive control to gain scheduling, where he's made very significant contributions, and more recently also in distributed systems, where we will learn a little bit about some very cutting-edge work on learning games today. So without further ado, welcome Professor Shamma.
Okay, thank you. Thank you, Professor Walid, for the invitation and the opportunity to participate today. I saw that the speakers have been giving a bit of an introduction to themselves, so I'll do the same, but I'll also give an introduction to KAUST briefly to just have an idea about the place, because it's a relatively new university established in 2009. The location, as mentioned, is in Saudi Arabia on the Red Sea, and it's right on the Red Sea here in this what used to be a fishing village called Thule. It's about 1 hour drive north of Jeddah. And this is what the KAUST campus looks like from above. It's in fact a closed community, so everything is on campus. The housing is on campus, the academics is on campus, schooling is on campus. There's a medical clinic on campus, and if you divide the campus up, okay, over here is a desert, here's a golf course, if you can believe it. I was reading that Halmstad claims to be the golf capital of Sweden, at least in the literature that I was browsing. So where's this is the academic campus here, and all of the buildings academic buildings are there. Town center means a handful of shops and restaurants and things like that. All of this community is actually residences, and so these are all homes. They have the golf course and a stadium, in fact. And they're trying to, if you will, reverse engineer a sort of a research park. So lots of either ranging from startups to multinational corporations are getting a foothold in the country and setting up small interactions with KAUST. And there's a particular emphasis on entrepreneurship, and that's the innovation cluster. It's a graduate-only university, so there's no undergraduate program. There are several undergraduate institutions, of course, in the country. So it's either master's or PhD or so-called MS PhD, someone coming in without a master's but intent to go on to PhD. To give you an idea of the numbers, right now there's about 1,000 students, 150 faculty, lots of postdocs and research scientists. You see it's very much geared towards a research campus, and this is what is envisioned once it's full size. So it's about 3/4 of the way, or 2/3 of the way to full size now. You see very much the bias towards a research activity. Okay, it's 80% PhD students, and then 20% students who've declared to be terminal master's students. So very much a research environment. Here's the breakdown between men and women. It's the only campus in the country where there's gender mixing, to comment on this 37% women at KAUST. That's about comparable to Georgia Tech graduate engineering. Okay, so it's something that's there and growing. And students are from everywhere. About 30% of the students are local to the country, and then you have many students from everywhere else. Middle East, North Africa. Yes, Middle East, North Africa. This terminology is a little bit hard to break down. I mean, it's understood that China's in Asia. But somehow it's not on the slide. Okay. Yes. Okay. It's a community, as I said, it's a self-contained community. There's 1,500 school children. I have 3 of them there. Alumni, community members, and it's a very national, multinational kind of a setting. And one thing that our president said about KAUST is that you go to, for example, a university in the U.S., and it's international in composition, but it's an American culture. Okay, it's American culture of operations. But here you have people from the Middle East, from East Asia, from Europe. A professor from Germany doesn't run their same group as a professor from Tokyo, as a professor from Santa Barbara. Okay, so you don't have you have an international or a diverse kind of culture of operations, which makes things interesting sometimes. It's divided, modeled after Caltech. So you have a biological and environmental engineering division. There are no official departments. We have programs, label them whatever you want, but there are no official departments. So there's biological and environmental engineering. There's physical sciences and engineering. And then there's this division, which I would call et cetera. And I happen to fall under this division. So computer, applied math, and computer engineering, applied math, and electrical engineering. And also KAUST has lots of research centers, and the research centers are, I think about half of the faculty belong to different research centers, and you see all of them are kind of emphasizing what KAUST started off with as its core areas of food, water, energy, and environment as the main kind of drivers of the research problems that we want to consider. And there's also supporting, these would be national labs anywhere else, just supporting labs where different faculty can tap into the resources that are there. And now KAUST is trying to let these resources be accessed within the country and the region as well. So I'll just click through these pictures. These are all just labs to support the different individual faculty endeavors. Visualization, supercomputing, workshop, of course, and then nano fabrication and the like. It's a young university established in 2009, so it's just now getting an alumni base. And you see we have now 1,200 alumni, about a little less than half work in industry, and then the rest are in academic institutions. A lot of our students go on to become maybe graduate students elsewhere or postdocs, so these are not necessarily all faculty. Where do students go? You see these are the main destinations of in the kingdom, back to the US, and then other areas as well. And again, this is a developing alumni. So that's KAUST. I'll give a brief bio about myself. I graduated in 1988. I was an undergraduate at Georgia Tech, graduate student at MIT, and I confess to having a short attention span. So I've moved around a lot. I was in Minnesota, Texas, UCLA, Georgia Tech, and now I'm in KAUST. I've been at KAUST since 2014, and I've had a chance to get a few distinctions. And now we have this, this is our logo, the Robotics, Intelligent Systems, and Controls Lab. And these are the emphasis of the different kind of directions, thrusts of the lab. And today's talk is going to be kind of mainly in this direction, related to this direction, the idea of distributed autonomous systems. And so with that, I'm going to switch over to the actual talk for the day. Okay, so game theory for cyber-physical systems. I struggled in preparing this talk in that I wasn't sure what's the audience, and so if you feel uncomfortable, I think I succeeded in will make everybody equally uncomfortable in this talk. Okay. We'll see. I'm gonna, I'm not gonna give the talk that I prepared necessarily, and then I think we can kind of go real time and assess, what's working, what's not working, and kind of tailor the talk around that. It'll be, I'm going to take advantage of that cyber-physical systems is not well defined, and so that automatically makes the game theory relevant. But it'll be mostly a talk about game theory and how it can be applied to engineered systems. So, this is if I had to give a definition of control systems, okay, this would be my definition of information-based decision-making in dynamic and uncertain environments. So I think not necessarily all of you would self-identify as a control person, but maybe you would kind of at least identify with this goal. What do I mean by information-based? It may be, these decisions are based on models, and that's a form of information. The decisions can be based on real-time data. Of course, controls has feedback, and feedback is a real-time information. And so controls is not just servo mechanisms and low-level controllers, but this reflects the kind of the breadth of control as applied to ranging from high-level decision making to low-level control. I found out that several of you are working on automotive controls, so you know better than I do about all of the different control systems that are inside a commercial vehicle, and all of you know the breadth of applications of controls as well. So the part that I want to emphasize now is the traditional architecture of control, because that's going to be a departure. This talk will be a departure from the traditional architecture. The traditional architecture is there's some system that we're interacting with, some environment, and what is a control system? Through available sensors, it senses what it can, makes some decisions, and then actuates through the actuators to influence the system that's being controlled. Okay, so this is the traditional architecture, and the main takeaway from the traditional architecture is two parts. There's central information. Whatever information is being measured real time, there's one entity that has that information. And central authority. Whatever actions that are being done, deliberate actions that are being done on the system, well, there's one actor taking those actions. So now this is these are covers of the IEEE Control Systems magazine. If you haven't seen this publication, the different societies within IEEE have magazines, so-called magazines, which are intended to be overviews that are more accessible to a larger readership than what might be the technical journal. So yes, there's an IEEE Transactions on Automatic Control, but it's not as user-friendly as the IEEE Control Systems magazine. And you see now these titles. Cooperative control, this is a picture of an experiment in ETH of many drones, many quadcopters building a tower. Social control, this was about how beliefs or information diffuses in a network, and how one can try to influence the propagation of beliefs. Control of infrastructure is all over the place. In particular, there's a lot of interest in these days in power systems and so-called smart grid. And but you see that what's happening here is a common feature is that there's multiple interacting agents. And that continues in this set of covers as well. Control of teams, and I know there's work in KTH then working on, and Lund on controlling fleets of trucks. The idea being that if they follow each other, then they can save on fuel, but you want to have them follow each other for at high speeds over long distances, to the point that it may be a human a driver can't do it reliably. Control of spreading processes, there's lots of models of things like epidemics evolving over networks, and where should one place the different countermeasures to stop the spread of an epidemic. And here we have special issue on distributed control and estimation of robotic vehicle networks. And again, we have many vehicles trying to do a mission, like, for example, a search and rescue mission. So you see kind of the running theme in all of those special editions is that the architecture doesn't really look like this anymore, but rather the architecture looks like this. There's some environment, and there's lots of decision-making actors influencing the environment, okay? So they need not share the same information. If we're a robot vehicle team, I see a different part of the environment than you see. And there is distributed authority. There's many actors influencing this system. And even, we might be part of the same team, but just because we're part of the same team doesn't mean we act as a cohesive unit. For example, we've played, in team sports, we've played, you see in volleyball, or that the ball will drop in between two players. Okay, and now they're on the same team. If there was one kind of coach controlling both players like puppets, that would never happen. But because two players are making their own decisions, there's some miscue. Or in football / soccer, you pass it to someone thinking that they're going to run, but they don't run, or thinking that they're open, but they're not open. We don't all have the same information. We are not all kind of making the same decisions in a coordinated way. So being on the same team in itself doesn't mean that we're going to act cohesively in the same way the traditional control architecture would do. In the traditional control architecture, you can think like there's a coach and there's players, but the coach controls everybody. The coach sees everything and controls every player. Whereas in this environment, players are making decisions for themselves. They have their own information. Maybe a coach can yell out a play, but it has to be executed by the players. And it turns out that this kind of architecture can behave very differently than that kind of architecture. So if I would summarize that, the decision quality of an individual is affected by the decisions of others. Okay? Whether or not it's a good idea to pass to an open location depends on whether the teammate's going to run to that location. Okay, otherwise, it's not a good idea to pass. So you have this kind of coupling of the quality of decisions. The decision of one player, the quality of that decision of agent or actor depends on the actions of others. So let me give some examples of such situations. This is some other work that was published a while ago in Transactions on Networking. The setting is as follows. You have a bunch of transmitting nodes, but they're using a shared medium, the air. And so they're transmitting, but when two nodes transmit at the same time, there's a collision, so there's not a successful transmission. Okay? What this graph represents is the interference graph. So if the two nodes are connected by a edge, that means that they can't transmit at the same time. Okay? So what the nodes are trying to decide is they're trying to decide on their probabilities of transmission. Day by day, I'm going to flip a coin according to a certain probability, and I'm going to decide whether or not to transmit on that day. Okay? And this paper considered this as a game. We're going to get back to what is a game later, but I'm just showing you the setup where the decision or the probability of transmission, what makes a good probability or a bad probability, depends on the probabilities of others. And there's different kind of criteria that one can assess whether or not they're doing a good job. We'd like throughput, we like lots of successful transmissions, but we'd also like some level of fairness. And the fairness means here, we can get successful transmissions by making everyone go silent and only allowing a couple of privileged to transmit. So that's not going to have fairness. So it's this tension between throughput and fairness. Here's another setting where, again, the decision quality of one depends on the decisions of others. This is in a file storage system, and actually this is work in KTH as well by Georgie Dan. So the setting is as follows. We have different file servers, and these file servers want to service a population. Okay? So I don't have room to store all of my files locally to service my own population, so I can store some of them locally. But if I get a file service request from that I don't have, then I need to get that file from somewhere. It's cheap to get it from a neighbor. It's expensive to get it from a central repository. Okay? So determining what files I should keep locally depend on what is my population requesting, but it also depends on what are my neighbors holding. Okay, so the quality of storing a particular file or not storing a file depends on what my neighbors, the files that my neighbors are holding. And so that's another kind of example of interconnected decision making, of the quality of a decision depends on the decision of others. It's not just a function of let me pick the most popular files in my own population. there's a lot of interest in so-called area coverage problems. So in area coverage problems, think of there's some region that there's some hotness map that we'd like to kind of send the sensors out to cover this hotness map. This hotness map might represent different things like an evolving plume in the ocean, or some released gases, or a enemy force that we want to monitor, all kinds of things. Okay. And so we have these sensors, and we want to send these sensors out so that they cover the map. The issue is that we don't know the map until we get there. Okay? It might be also that this area might have some kind of geometric structure. So there's an underlying graph that represents where can we go and where can we not go. And we'd like to send our sensors out so that they cover as much of the graph or as much of the map as possible. But whether or not it's a good idea to cover a location depends on who else is there. Because we don't want redundancy, we'd like to kind of spread out the coverage. So again, a decision here is where should the sensor sit? Sitting at a particular location depends on where other sensors are sitting. So you see on all of these examples, we have this repeated kind of structure that what makes a good decision depends on the decisions of others. And we'll come back to these different applications. So I've been repeating this feature. Decision quality of an individual is affected by the decisions of others, and that leads us to game theory. Okay, so here's a definition of game theory from a book called Game Theory. The study of mathematical models of conflict and cooperation between intelligent, rational decision makers. So the key word here is between intelligent, rational decision makers. Now we can debate what is intelligent, and we can debate what's rational, and in fact there is a lot of debate about what's intelligent and what's rational, but I want to focus on the between part, and that's the quality of a decision depends on what others are doing. Okay? And in fact, there's been a lot of work, at least in the communications community, employing game theoretic methods. So here's now, these are not papers, these are monographs. These are not covers of magazine articles, these are monographs. It's developed to the point where you have several monographs exploring the role of game theory in communication. So game theory and learning for wireless networks, network security, a game theoretic approach, game theory and wireless communication networks, game theory for wireless engineers, and network games. Okay, it's and you can think in networks, it's a very natural setting because you can associate, as we saw with the shared medium access problem, the players or the actors as the individual nodes of a network. So there's been a lot of work, in fact, exploring the role of game theory. But one caution is that traditionally game theory was not about engineered systems. Okay. Game theory came out of actually social sciences more than the engineering sciences. So, the application of game theory has to be a cautious one in that we're talking about engineered devices and not people. Okay, so going forward, we should kind of remember that cautionary statement. And so that, one way to describe that is that we're talking about a descriptive agenda rather than a prescriptive, a prescriptive agenda rather than a descriptive agenda. The descriptive agenda is we're making models of different situations, okay? And we're using game theory to understand or develop insights into what is going to be the outcome of the situation when we have multiple decision makers. The emphasis is on insights. The emphasis is not necessarily on actually kind of having a design tool. Okay, now there are some notable exceptions where game theory is used as a design tool. Most recently, there's lots of work in auctions and the role of game theory in auctions. Again, an auction is a game. Why is that? Because the quality of my bid depends on the bids of others. My satisfaction with my bid depends on the bids of others. So there's a lot of work on how do you design auctions to induce a desired effect. It's not necessarily all about the revenue. There are many kind of things that one can try to do in designing an auction. Another case where game theory has played a significant role is in so-called matching problems. For example, you want to match students to schools, you want matching residents to hospitals, matching organ donors to organ recipients. That can be formulated in game theoretic terms, and if we have time, I might talk about matching problems a bit. So, but the main point I want to make here is that game theory is often used as a as to develop insight, not necessarily to build a system. And there's one quote that I really like that kind of that captures the kind of intent of a lot of game theoretic models is this one. So the word model sounds more scientific than the word fable or tale, but I think we're talking about the same thing. Okay. Think about how we talk about models. I mean, we had a talk on model-based engineering, and what our intent was. We were asked, we were challenged, what's the role of the model in model-based systems engineering? The role of model here is very different. Okay, so you know what a fable is, right? A fable is the story. It's not a realistic story, but the story has a moral. Okay, and the moral, and that's the lesson learned from the story. So we've all heard the story about the tortoise and the hare, right? The turtle and the rabbit. And so what if I tell you the story? What's the lesson? Anyone remember the lesson of the tortoise and the hare? What's the takeaway from that?
Perseverance.
Perseverance. Okay, you didn't say who was the timekeeper. I don't believe this model. It's not realistic. You know, where did they train? How did they communicate? You didn't say that. You said slow and steady wins the race. Perseverance. So the model is a fable, okay? But it parallels reality. And the lesson, the moral from the fable is applicable to reality. Most game theoretic models are like that, okay? So don't come and say that's not realistic. And yet, we want to use this kind of game theory to design engineered systems. Now, we're encroaching on realism. Can we use game theory to design as a design tool when it wasn't really meant to be that? Okay, it was meant more as a kind of, I think this again, if we're going to stick to this quote, to more as a stylized, idealized representation of reality from which we can extract insights. So, there are 3 lectures, and there's intended to give 3 parts. And like I said, we'll figure out what we'll cover and what we won't cover in real time, okay? Because the lecture that I prepared is unsuitable. But it has suitable parts, and we'll see if I can extract these suitable parts. So we're going to have a brief introduction to game theory, then we're going to shift the emphasis to something called learning in games, and we're going to see how we can apply these to multi-agent systems. And here's a lab demo to show like what happens when we put all of these pieces together. This is from my old lab in Georgia Tech. And what we have here is just a kind of a sensor coverage problem in a varying environment. Now what these mobile units want to do is cover the hot region. You and I, we can all see where the hot region is from above, but they can't. So they can kind of see what's in their circle of a sensing circle, and they can also get a sense of who's nearby. Okay, but nobody has a global view of the environment. This agent can seize what's here and also gets a sense that there's another sensor close to me, or we overlap, so I have a sense of when there's an overlap between me and someone else. And then, so this is all, the tools that I'll talk about today. By the end of the lectures, you'll be able to code this in a pretty straightforward way. We're going to formulate this problem as a game where the players are the different sensors, and then devise a strategy so that they execute coverage. Now you might see this one wandering off. It looks like they're lost, but for all they know, there's another hot region over here. Okay, we know that there's not because we see it from above, but they don't know that. So you've all heard the expressions of exploitation versus exploration. Well, that's an exploration part, okay, of looking for other stuff. The exploitation part is covering what I know, and we'd like to balance the exploration versus exploitation so that we do effective coverage while still never turning off the exploration. And as I said, this is a game theory algorithm, just extracted, modified to suit our needs, and applied to this setting, which I'll take the liberty of calling cyber-physical. All right, what do you do in a game theory crash course? You start with a game. So here, I have 1, 2, 3, 4. piece of paper. Just take one and pass it down. 1, 2, 3, 4 piece of paper. Pass it. Take one and pass it down. All right. So here's the game. Everybody's going to pick a number between 0 and 100. I'm going to gather these numbers. I'm going to take the average of these numbers and divide the average by a half. Whoever's closest to the average divided by the half is the winner. So it's clear? You pick a number between 0 and 100. Everybody give me your numbers. I'm going to take the average. Whoever's you didn't even know the rules before you put a number. Okay, try again. You got it? Okay, all right. I'm going to take the average, divide the average by a half. Whoever's closest is the winner. Okay, so I'll take them.
You can easily find out which year they born.
All right. Is that everyone? Thank you. All right, so let's put up the numbers here. Okay. Well, you'll remember your number. 13.
I could cheat.
0. Okay. 25. 0. A lot of cheaters here. Somebody put 0.0001. I'm going to take the liberty of putting 0, okay? Okay. 48. 50. And 41. What's the average? Can anyone help me out with that?
25. No. Mean or the mean?
So we have 13 plus 0 plus 25 plus 0 plus 0 plus 48 plus 50 plus 41 divided by 8. Yay, 22. So who's right here? 25, winner. Okay. All right, good.
Who's the winner?
Okay, good. Very nice, very nice. Now, some of you cheated and put 0. And let's talk about that. Pardon me?
Isn't it more clever than cheating?
You lost. Who are you talking about? Really?
Pointed behind the
You
Russian
lost.
agents, right?
Okay. Yeah. Tell me clever and he lost.
Losing is not cheating.
Oh, that's not why he cheated. He knows why he cheated. Okay. All right. So if you put 100, I mean, the only 50. The only way to win at 50 is if everyone else said 100. Okay. So this was a curious one. This was also a curious one. We're going to come back to why that's a curious one. And 0 is also a curious one. But tell me, if you put 0, or even if you put 0.0001, why did you do that? So why did you put 0?
If everyone takes a random number, then we would have something like 50, right? As the average. Half of that is 25. So everyone was supposed to have something like 25 as their solution because they want to be close to this number. And if everyone does that, then the average would be 25. So half of that would be 12.5,
Okay.
right?
Yep.
And this would diverge. That would converge to a really low number. So you should have something like 1.
Okay,
0.
so what you just invented was level K reasoning in game theory.
Right.
That's a keyword, level K. So the other zeros similarly derived. How about the 25?
I saw that most of us will take 5 numbers. So we almost near 100 or 80. So take numbers between 10 and 100. So if we take the average, it would be in the same area. So if we divide it into half,
Okay.
it would be around 24.
So a level 0 person would pick a random number, and then level 1 would say what's optimal against level 0. And so you modeled everyone else as level 0, and then you modeled everyone else as actually very high level. Okay, so we're going to come back to this. All right. The reason, this is actually called the beauty contest, and there's a reason it's called the beauty contest. It came from actually newspapers. I'm not going to put the same pictures up. But if I asked you who's your favorite character, and whoever picks the most favorite character is going to be amongst the group of winners, then are you going to pick your favorite character, or are you going to pick who you think other people will pick? Okay, and so it starts making you think about, we really don't have any preferences between numbers 0 to 100. They're all numbers. But what made us have preferences is depending on what others are going to do. So the beauty contest was, here pictures of attractive individuals, and you need to guess who's going to be considered the most attractive, and then that enters you into a lottery or something like that. If you're thinking about stock market, one model of stock market is not so much about whether I think this is a good company, but whether I think other people will think this is a good company to drive the stock up. Okay, definitions. We have, in a game, we have a group of players, and these players have choices, and these players have preferences over joint choices. Joint choices. If I said to you, you just played the beauty contest game, do you like 17 or 18 better? Do you like 20 or 50 better? You don't have a preference over your own choice. It depends. Your answer will be, it depends on what others did. So you have preferences over group decisions. Okay, and there's different group outcomes that you prefer over other group outcomes. Okay, those are the basic elements of a game. Now, how do we express preferences? Well, maybe we can say, if the group did this, I like it better than if the group did that. Okay, just some sort of ordering. But oftentimes, preferences are expressed through a utility function. Tell me what everybody did, and I'm going to give it a score. Bigger is better. Okay, one can try to express the preferences in that way. Of just tell me what everyone did, and I'm going to give it a score, and that way I'll say that the group action is better than this other group action if the score, my utility function, is higher. Okay, so here's a very famous game, the so-called Prisoner's Dilemma. It's a two-player game, and the way you read this is that there's two players. There's a row player and a column player. And they can have a choice of whether or not to cooperate or defect. So this is their choice, cooperate or defect. The way you read these numbers is that the first number goes to the row player and the second number goes to the column player. Okay? So that's their utility. If they both cooperate, each one gets 2 points. If the row player defects and the column player cooperates, the row player gets 3 and the column player gets 0, all the way around. The story of the Prisoner's Dilemma, and this is this 2x2 matrix has launched 1,000 ships. Okay, the story is that two prisoners are being interrogated. If they both stay silent, they'll do well. But if one stays silent, the other one accuses the other. The accuser now defected. They betrayed their agreement. Okay, and now that the defector is rewarded, whereas the one who stayed silent has a more severe punishment. Or they might both say the other one did it, and then they both defect. Okay, who's the winner? You were the winner?
Yeah.
What would you do? Let's play the Prisoner's Dilemma. Okay, here, you can write it. I'll write mine. Okay. You pick cooperate or defect, yeah.
What?
You need to pick C or D.
Okay.
All right, let's see. Oh, that's cold. He defected. He chose to accuse me. I defected too. All right. We can come back to the Prisoner's Dilemma later. All right. So these are all the elements. And you see that here we express utility functions, but the row player says, this is my group outcome. My favorite group outcome is when I defect and they cooperate. My next favorite is when we both cooperate. My next favorite is when we both defect. My least favorite is when I cooperate and they defect. But you see, it's preferences over group actions, and then we kind of represent that as a score. Now, there's lots of these kind of simple 2x2 games that are meant to be tables. Okay. For example, this is the game of aggression. If we're both aggressive, we destroy each other. If one of us is aggressive, whereas the other one is passive, the passive one only gets 0 points. The aggressive one gets 4 points, but that's better than we destroy each other. And it's symmetric. And if we're both passive, then we both get 1 point. Okay. Stag hunt, that's meant to be another fable. what does it mean to cooperate or to coordinate? The stag means deer, and H stands for hare or rabbit. If we both hunt for a deer, we can catch a deer together and take home half of the deer. Okay? However, if I go to hunt for a rabbit, I can catch a rabbit without your help. Okay? So should we coordinate? Apparently these are very big rabbits, okay, because 3 is half a deer and 2 is a rabbit. But should we coordinate or not? Because I have some risk. If I go out deer hunting and you don't show up, I go home empty-handed. Okay, so if we coordinate on deer, we'll be better off, both of us, but there's some risk associated with that coordination. There's a similar thing with technology. Sometimes there's one technology that's superior to another technology, but we have to be using the same technology to be able to take advantage of that. What does it take, and in particular, what does it take in a network so that we can kind of have a so-called tipping point? If we're all using the inferior technology, how many need to use the superior technology before we can migrate the population to use the superior technology? These are all examples of games. There's a comment? Yes?
In all these examples, do you assume that all players know how to do the whole table, or is it that they may not know about it?
All of the above. There's each case is a different setting. Yeah. Okay. So I can have full information about the game, but even then, like for example in stag hunts, there's the coordination part. So I have to have a belief that you will play a certain action. Okay, even if we have full information, but then there's partial information and yeah, all of the above. Okay. Here's a type of auction where we want a limited resource. So I'm going to put in a bid to get access to the resource. How much of the resource do I get? I get my bid divided by the bids of everybody. So that's the fraction. So if I bid a certain amount, I'm going to divide it by everybody else's bid, and that's the fraction of the resource that I'll get. And this is how I value the fraction of the resource that I'll get, but I end up having to pay my bid. So this is my overall utility function. Routing, okay, here we're minimizing, not maximizing. I need to figure out what path to take from A to B. The quality of my path depends on the paths that others take. Do I take a congested road? There's some roads that are shorter, but they're more susceptible to congestion. So the quality of a path depends on the path that others take. And let's see, I'm out of time, huh? I got about 3 more minutes. All right, let's see what to do. When we formulate a game, we'd like to model what's going to happen, okay? What is going to happen? And here's something, you may have heard this, Nash Equilibrium. This is the famous model of what's going to happen. A model is everyone is acting optimally with respect to everyone else. So if when we play a Nash Equilibrium, suppose we all picked a particular choice. I'm going to go around the room one by one and saying, this is what you did, this is what others did. Are you happy with your choice? Okay? For example, here, is this a Nash Equilibrium? It's not, okay? Because whoever is the high number says, I wish I picked lower. The high number will never win this setting, right? So the high number will always wish that they picked something smaller. So this is not a Nash Equilibrium, okay? But Nash Equilibrium is a model. By the way, what do you think is the Nash Equilibrium of this game? Everybody picks zeros across the board, okay? That's the only way that nobody will regret their action. But it is a model. And, you know, I want to make it where modeling everybody is acting optimal with respect to everybody else. And that's a curious model. So, you know, we're all here, you know, engineers, and we're used to optimizing, right? So we can take a course in linear programming or convex programming or dynamic programming. What does that mean? There's some choice set, there's some utility function, and we want to learn how do we maximize our choice, maximize utility over our choice set. And depending on the structure of that problem, we do different things, okay? Now, forget about games. Suppose you're looking at somebody making a choice. Would you model them as an optimizer? Would you model them as doing what's optimal for their situation? First of all, I want you to recognize that that's a different question. Finding out what's the optimum is different from modeling someone what they're going to do, okay? And for example, suppose that the problem that they're trying to solve has a high computational complexity. Okay, so a supercomputer can't figure out what's optimal. Are we going to model this individual as doing what's optimal? Suppose there are parts of the decision problem that haven't been fully specified, and I can give you examples of these. So, it's known that people will give different answers to the same question depending on how the question is phrased. Okay, they come up with a different decision. So how do you model if the framing, the way the question is posed, has nothing to do with computing an optimizer? Okay, so would we model decision makers, even one decision maker, forget about games, as a optimizer? I was going to give an example of where modeling a decision maker is difficult, and these are, I think, let me finish these two examples. It's light, it's not about games, but it's really revealing about how hard it is to model someone. Okay, so here's the setting. There's a box of colored balls. You're going to make a decision. It's not a game. You have to make your own decision. There's no right or wrong in this decision. We know that 30 of the balls are red, and the other 60 balls are some color, either green or blue, some mix of green and blue. They could be all green, they could be all blue, they could be half and half, whatever. But you know for sure 30 of the balls are red. There's a total of 90 balls in the bin, in the barrel. Okay, now you need to make a bet. Which would you bet on? I'm going to reach in the barrel and pull out a ball. Would you bet that I pull out a red one, or would you bet that I pull out a green one?
Red one.
Red one? Red one, why? There's no right or wrong answer. Just it's your money. Okay.
Because I have some read information about the red ones, I have some read number,
Okay.
but I'm not sure about the green ones.
Very good. Okay. How about this? Would you bet that you win if it's either red or blue?
Mm-hmm.
Here you win if it's green or blue. Green or blue, how many green or blue are there?
60.
60. Which would you bet on?
Green or blue.
Green or blue. Okay, very good. So he's going to bet on red versus green.
Mm-hmm.
Another way of saying that is that you think there's more red than green.
Mm-hmm.
If you think there's more red than green, then you should think that there's more red-blue than green-blue.
I'm not sure the total number.
Wait a minute.
of green.
Do you think there's more red than green? Yeah, you just bet on it.
Yeah.
So you should think that there's more red-blue combos than green-blue combos, because blue cancels out. Okay, so that's why this example is famous. All right, it's called the Ellsberg Paradox, and it illustrates an inconsistency in when there's information that hasn't been fully specified. Okay, and the way we process uncertainty is different. This is just illustration of how it's difficult to model the decision of an individual. Okay, and that's the so-called Ellsberg Paradox. This will be my last slide, and then we'll see what to do for the next two talks. This is another behavior that's been witnessed. Okay, I offer you beef or chicken. You say, I'll take beef. I said, oh, I'll offer you beef, chicken, or fish. You say, I'll take chicken. All right? And, this seems outrageous, but it happens, okay? Not necessarily with beef, chicken, or fish. I mean, suppose I said, I'll offer you beef or vegetable. You say, I'll take beef. But suppose you say there's beef, vegetable, or, iguana, okay? Maybe you'll switch to vegetable. Okay. Okay. So it says that we don't always make decisions by doing pairwise comparisons. The presence of a third alternative may switch our preferences on the first two alternatives. This is a phenomenon called independence of irrelevant alternatives. This example shows that we don't have independence of irrelevant alternatives. The presence of a third option shouldn't change our preferences here. The point is that this kind of behavior cannot be represented by a utility function. So my point here is that modeling a decision is difficult when it's even one agent. Modeling decisions when it's groups of agents interacting is all the more difficult. And Nash equilibrium, everyone's choice is optimal given the choices of others. Well, optimality is controversial even when there's one agent, let alone many agents. So, but it's what we got. And with that, we'll end the first part of the talk. Okay, thank you.
Questions?
One question. Here you don't in this model there is no notion of time like when I make the decision or if I make decisions in a staged way. Does game theory also try to address this issue?
So here, if you look at it in its generality, I just said there's a choice set. So for example, my choice might be my controller. Suppose you had a system that had two controllers, okay? And that controller is a dynamical system. My choice is what controller should I use? And the controller is how am I going to react to information as I receive it? So it's not so much I'm going to cooperate with the fact I'm going to pick this number or that number. My choice might be my reaction rule. How do I behave when I see get different information? In that case, the choice set is huge. My choice set is over the set of all dynamical systems. But at least in form, it fits here. Okay, so if the game is evolving in stages, for example, like chess can be a game, a zero-sum game. What is my choice? My choice is not so much move this piece or not. My choice is how do I map the board to a move? That's my choice set, my method of play, my reaction rule. That's my choice set. And you're going to measure one person's reaction rule versus another person's reaction rule and see which one will win. It's not about the piece movement, but how I react to situations. So game theory, it's deceivingly kind of simple, at this stage, it's deliberately we're sticking to simple settings, but it can be very involved on what game theory can accommodate.
Okay. Any other questions from the audience? I have a quick question, actually, just a quick show of hands. How many people have come across game theory before? Okay, quite a few. And how many people are familiar with Nash Equilibrium for simple games, for example? Okay. So a few people. All right. So
I have another question to follow up.
Yeah.
For those of you that knew that zero is a Nash equilibrium, did any of you not pick zero?
Good question.
Okay. So you knew it's zero, but
I did the 0.001.
okay. 1 0.
Like predict how many other people,
Yeah.
like somebody will pick 0, right? So it should be a little bit higher.
But anyone else knew that the Nash equilibrium is 0 but didn't pick it anyway?
I did.
What did you pick?
I picked 13.
13. So you were another
level 1.
level 2.
Level 2.
Level 2.
Yeah.
Yeah.
Is there psychological studies that show where we, as human beings, typically how deep we can reason?
So I have a chart that shows, and this is related to how we apply game theory to cyber-physical systems, that now if we had the time, I would ask you all to play it again, and then play it again, and then play it again. And what you see is a convergence towards everyone playing 0. So the Nash equilibrium might not have been a good model of what happens in this decision setting, but it might be a good model of what happens when players repeatedly play the same game. And then there is experimental evidence that shows people's plays are, for the experimental evidence, and I'll bring up this chart in a later talk, it shows two things, that choices are clustered around these levels. So there's a cluster at 25, there's a cluster at 13, and as they play more and more, there's a drift towards 0. But that is an active area of research, so-called behavioral economics, and there's lots of game theory labs where they put people in in a room and let them repeatedly play to try to model how the decisions evolve.
If I may, are you suggesting that initially we'll all play around level 1, and then as we play on, we will
I'm not making that strong of a statement. I'm saying that they at least with the experiments that I've done in this game, there's a clustering and a drift. The initial one, I'm not sure.
Do the participants know about this theory, or are they just random people put into the room?
And now you're bringing up some very interesting points. Okay, that you know, if I say, you know, just grabbed passersby and asked them to, suppose I was able to grab passersby and say, play this game.
Yeah,
but now my passersby, I'm at Caltech, right? And so you know, so you bring up an interesting point of like, who knows what? Am I going to see you again? Do I have opportunity of colluding? You know, there's lots of issues that come up in experimental game theory of how do you make the experiments kind of pure. But you know, I have a confession. You know, so all of us here are engineers, right? We're all techies, and we're not so-called fuzzies, okay? And fuzzies, you know, yeah, the fuzzies, we say, oh, you know, they work on. I say they, like my son's a fuzzy. Okay, he works in communications, and people say, oh, he works communications here. No, this communications. Yeah, and so you know, because you can't do repeatable controlled experiments. You don't have first principles like Newton's law to guide your designs. But as you know, time went on and I became exposed to game theory, I found that exactly those kind of features make it all the more intriguing. If I still have to design a system where I can't do repeatable controlled experiments and I don't have first principles to guide the design, that makes it all the more interesting. And I think that's where controls may have something to say, because controls is about you know, decision making under uncertainty, and what's more uncertain than you know, groups of human decision makers. But the, you know, experiment design is a big deal.
So does game theory assume that everybody is rational? So because in real society, not everybody is rational.
Yeah, so that's an issue. We want to model the outcome. So the Nash equilibrium was everyone's rational. We saw that's not the case. And so then there's a whole literature on so-called bounded rationality, and you know, the objective is again to model how decisions will be made. Yeah, so yeah, a large body of game theory does stay under the assumption that everyone's rational, but then there's a large body of game theory, and that's actually topic number 2. Is it possible that non-rational, not by non-rational, I mean not fully rational, but simple-minded, can simple-minded agents through interaction go to a highly rational outcome? Okay, and that's what's called learning in games. Okay, and this was the second intended talk. Okay.
Is that different from like swarm intelligence?
Now that's that's the third slide now. The third talk is how can we use that to do things like swarm intelligence. Okay. So I think I did a good job of conveying what I would have liked to talk about. We'll see how much of it I get to. Okay.
Thank you very much, Jeff.